Have you ever, stopped to think about the invisible battles happening inside us all the time? Sometimes our body needs help, right? Powerful allies. So how do we actually fight back against these tiny invaders, these pathogens? Welcome to the deep dive.
Today, we're getting into the really critical world of antimicrobial agents. And look, this isn't just memorizing drug names. It's about truly understanding how these vital medicines work, what they can do, how we get them where they need to go, and, yeah, the big challenges they pose, too. It's foundational stuff, pulled from reliable medical sources, knowledge you'll definitely use.
Absolutely. And our mission here really is to equip you with the whys. Why do clinicians make certain choices about infections? We want you to grasp the core concepts, remember the key details, and develop that critical thinking you need for antimicrobial therapy.
Okay, so let's set the scene a bit. Think back to Paul Ehrlich, late 19th century. He had this idea, this vision of a magic bullet, a chemical that could, zero in on pathogens and destroy them, but leave our own cells unharmed. Such a radical idea back then. Revolutionary, really. And then much later, you get Sir Alexander Fleming's discovery. Almost accidental, wasn't it? Penicillin.
Yeah.
A fungus making its own weapon, and suddenly humanity has a real magic bullet. Changed everything for treating infections.
Totally changed the game. So as we start this journey, here's something to think about. If you were designing the perfect antibacterial drug, what's the one single characteristic it would absolutely have to have? Keep that in your back pocket. We'll circle back to it. All right, first things first, let's nail down some terms. People often use these words, well, interchangeably, but medically there's a key difference. We have antimicrobial, that's the big umbrella term, right? For any substance, natural, synthetic, whatever, that kills or stops microbes with minimal harm to us, the host.
Exactly. It's the broad category.
But then there's antibiotic.
Yeah.
More specific. What's the key thing there?
Yeah. That's interesting. All antibiotics are antimicrobials. But it doesn't work the other way around. Antibiotics are a special group. They're specifically low molecular weight substances produced by a microorganism that kill or inhibit other microorganisms.
Okay. So it's like microbe on microbe warfare, naturally occurring.
Precisely. Nature's own chemical arsenal. You see organisms like Streptomyces, Bacillus, Penicillium producing these things to, well, compete for resources.
Makes sense. They're fighting for their turf.
They really are. It's a constant biological arms race. And that brings us right back to your question about the perfect drug. Ideally, an antimicrobial would tick a lot of boxes.
Yeah.
Microbicidal, a killer, soluble, potent, stable. It wouldn't trigger resistance easily. It would help our own immune system get into tissues, reach the infection site, be affordable.
A long list.
A very long list. And not cause allergies or secondary infections.
Yep.
But the absolute most critical thing, the one you asked about, tying back to Ehrlich's magic bullet, it's selective toxicity. The ability to hammer the microbe, but leave our host cells alone. That's the cornerstone. Without it, you're just causing harm.
Selective toxicity.
Right.
That's the goal. So in a perfect world, diagnosis would be simple. We'd get a sample, grow the bacteria, see what kills it, pick the exact right drug. Easy. But the real world, especially with someone really sick, maybe with sepsis, you don't always have that time, do you?
Not at all. Time is absolutely critical in those situations. So often, we have to start with what we call empirical antibiotics. This means giving broad-spectrum drugs right away before we know the specific bug. It's a calculated guess, based on likely pathogens, to buy time.
An educated guess when the clock is ticking.
Exactly. It's very different from targeted antibiotics, which is what you use when you do know the enemy and its specific weaknesses.
Okay, that makes sense. You go broad when you have to, targeted when you can. Now, thinking about strategy, when bacteria invade, do we always need to, completely wipe them out? Or is it sometimes okay to just slow them down, stop them multiplying, and let our immune system handle the rest? Think about this. You've got a patient, severe infection, life-threatening, and their immune system is compromised. Which approach do you take? The killer drug or the staller drug? Why?
A really fundamental question. This brings us to bactericidal versus bacteriostatic agents. You can think of them as the killers versus the stallers. Bactericidal drugs, they're the killers. They actively destroy the bacteria. It's usually irreversible. Examples are things like penicillins, cephalosporins, aminoglycosides, quinolones.
The heavy hitters.
Right. Then you have the bacteriostatic agents, the stallers. They don't necessarily kill. They inhibit growth, slow down replication. It's reversible. Take the drug away, they might start growing again. Think tetracyclines, sulfonamides, macrolides, chloramphenicol.
Okay, killers and stallers.
So to answer your question about the severely ill, immunocompromised patient, you absolutely go for the killers, bactericidal agents.
Why specifically?
Because their action doesn't depend so heavily on the patient having a strong immune response to clear the infection. The stallers need a working immune system to finish the job, basically. And your compromised patient might not have that.
That clicks. Killers for when the body's own defenses are down. But, just playing devil's advocate, are there times when a staller might actually be better, assuming the immune system is okay? Is there a downside to always going for the kill?
That's a great point. It's not always about maximum killing power. Sometimes bacteriostatic drugs have advantages, maybe in less severe infections, or if you want to avoid a massive release of toxins when bacteria rapidly killed something called lysis, it can cause a big inflammatory reaction.
Ah, okay, so sometimes slowing them down is less disruptive?
It can be. It lets the immune system manage the cleanup more gradually. You might also get fewer drug side effects sometimes. But the trade-off is you need that competent immune system. And it's also worth remembering, some drugs can be both static and cidal, depending on the dose, how long you use it, even the bug itself. And then there are bacteriolytic drugs, too, which kill and make the cells burst open.
Wow, okay, so it's quite nuanced. Right, let's move on. If we're attacking these bacterial fortresses, we need to know their weaknesses, their vulnerabilities. What are the main targets our drugs go after?
Good analogy, the fortress. Yet generally, antibacterials exploit about 5 main weak points or mechanisms. They interfere with cell wall synthesis, protein synthesis, nucleic acid synthesis, critical metabolic pathways, or they disrupt cell membrane function.
5 main targets. Let's take the first one. Inhibiting cell wall synthesis. We know that wall is crucial for bacteria. So here's the question again, slightly different angle. If these drugs hit something so vital to bacteria, why are they usually pretty safe for us humans? Low toxicity, you said.
Yes, and the reason is beautifully simple, actually. It comes back to that selective toxicity. Human cells do not have cell walls.
Right, we have membranes, but not that rigid outer wall like bacteria.
Exactly. So targeting something the bacteria have, but we lack, makes these drugs highly selective. It's a fantastic therapeutic window. Think of that bacterial cell wall like, well, the bricks and mortar holding their structure together under pressure. Damage that, and the whole thing collapses.
That difference is key. Does that basic principle find something unique to the bug guide, how we look for new drugs too?
Absolutely. That's the gold standard for drug discovery. Find a target essential for the pathogen, but absent or significantly different in the host. That's how you get a magic bullet. A prime example for cell wall inhibitors, the beta-lactams, big family. Penicillins, cephalosporins, carbapenems, monobactams. They mess with enzymes called PBPs, penicillin binding proteins. These PBPs are like the construction crew, cross-linking the peptidoglycan strands to build the wall.
The bricklayers.
The bricklayers, exactly. Beta-lactams bind to them, stop the construction, the wall gets weak, and the cell basically falls apart or bursts from osmotic pressure. The core structure doing this is the beta-lactam ring.
But bacteria fight back, don't they?
Oh, they do. Clever little things. They can produce beta-lactamases. These are enzymes that act like molecular scissors, snipping that vital beta-lactam ring. Drug becomes useless.
So we have a countermeasure.
We do. Beta-lactamase inhibitors. Things like clavulanic acid. We often combine these with a beta-lactam antibiotic. The inhibitor acts like a bodyguard, sacrificing itself to the bacterial enzyme, letting the antibiotic sneak through and do its job.
Like a shield. Clever. Are there others that hit the cell wall?
Yep. Glycopeptides like vancomycin, also bacitracin, they interfere with the wall-building process too, just in slightly different ways.
Okay, so we've attacked the wall. What's another major vulnerability inside this bacterial fortress?
Target number 2, inhibiting protein synthesis. Think of bacterial ribosomes as tiny, absolutely essential protein factories. They make everything the cell needs to function.
And our cells have protein factories too, obviously.
We do, but here's the key difference again. Bacterial ribosomes are structurally different. They have 30S and 50S subunits making a 70S ribosome. Human ribosomes are 40S and 60S, forming an 80S ribosome. That difference in architecture is enough for our drugs to target the bacterial factories selectively.
Different blueprints for the factories. So how do the drugs jam up their production lines?
Several ways. First, aminoglycosides, gentamicin, streptomycin, they bind to the 30S subunit. What they do is cause a misreading of the mRNA code, so the factory starts churning out faulty proteins, junk, basically, that can't do their jobs. Gums up the works.
Making garbage instead of useful stuff. Got it.
Yeah.
What else hits the 30S?
Tetracyclines, like doxycycline. They also bind the 30S subunit, but reversibly. Their trick is blocking the docking site for tRNA transfer RNA. tRNA is what brings the amino acid building blocks to the assembly line. Block that, and you starve the factory of its raw materials. Protein synthesis grinds to a halt.
So one makes bad products, the other stops supplies. What about the other part of the ribosome, the 50S?
Right. That's where macrolides like azithromycin and erythromycin and also chloramphenicol come in.
Yeah.
They bind to the 50S subunit. Their action prevents the ribosome from forming peptide bonds, the links between amino acids. So again, you stop the protein chain from growing. Halts production.
Okay, hitting protein production hard. Let's move to target 3. Inhibiting nucleic acid synthesis. Bacterial DNA is supercoiled, right? Like a tightly wound up hose pipe. It needs careful unwinding and rewinding for replication, making RNA basic life functions. Mess that up and you're in trouble.
Absolutely critical process. And the drugs that exploit this are the quinolones, like ciprofloxacin, levofloxacin. They inhibit bacterial enzymes called DNA gyrase and topoisomerase stafase. These enzymes are the masters of managing that, supercoiling, the untangling experts, if you will.
Right, they manage the twists and turns.
Exactly. Block them, and the bacteria can't properly replicate their DNA, can't transcribe RNA. It shuts down their core operations, stops growth and division.
A direct hit to their genetic machinery.
Yeah.
Okay, what's the 4th strategy?
Fourth strategy targets metabolic pathways. The idea here is that bacteria often have unique biochemical assembly lines for making essential molecules that humans either don't make or we get them differently, usually from our diet.
Like folic acid. I remember something about that.
It's exactly like folic acid or folate. Bacteria have to synthesize their own folate from scratch. Humans, we get it from food. Big difference. So drugs like sulfonamides, part of cotrimoxazole, for instance, exploit this. They look chemically similar to PEBA, a precursor molecule bacteria use to make folate. They act as competitive inhibitors, blocking the enzyme dihydropterone synthase so the bacteria can't use PEBA to start making folate.
Blocks the start of the assembly line.
Right. And then you have trimethoprim. It inhibits a different enzyme, dihydrofolate reductase, which acts later in that same folate pathway. Using sulfonamides and trimethoprim together delivers a potent 1-2 punch to bacterial folate synthesis. Very effective synergistically.
Clever. Block the supply chain at 2 points. Okay, what's the 5th and final target?
The last major target is disrupting cell membrane function. These drugs basically poke holes in or destabilize the bacterial cell membrane. This causes leakage of essential ions and molecules, disrupting the cell's internal environment and leading to death.
But hang on, human cells have membranes too. Does that make these drugs riskier?
That's the crucial point. Yes, it raises a caution. Drugs like polymyxin B, which target the membrane, can be less selectively toxic because fundamentally all cells have membranes. While there are differences in composition, the similarity means there's more potential for host toxicity. That's why these are often restricted to topical use creams, ointments, rather than being taken systemically. Reduces the risk to our own cells.
Okay, that makes sense. So those are the 5 main ways we attack bacteria. Really diverse mechanisms. Now, knowing how they work leads to who they work against. Let's talk about the spectrum of action. How broad or narrow is their aim? Like using a sniper rifle versus a shotgun.
Good analogy. Yeah, we classify them based on their range.
Yeah.
Narrow spectrum agents are like the sniper rifle. They're active against just a single type or a very limited group of microbes. Think isoniazid, mainly for mycobacteria, or vancomycin, most gram-positives, polymyxins, mainly gram-negatives.
Very specific targets.
Then you have extended spectrum. These hit gram-positives, plus a decent range of gram-negatives. Ampicillin is a classic example here.
Wider reach.
And finally, broad spectrum. That's the shotgun. Active against a wide variety of bacteria, both gram-positive and gram-negative. Examples include tetracyclines, chloramphenicol, the flora quinolones, and the later generation cephalosporins, like 3rd and 4th gen.
Got it. Narrow, extended, broad.
So once we've chosen the right drug with the right spectrum, how do we actually deliver it, get it to the battlefield?
Right, routes of administration. We can give them orally, pills, liquids, intramuscularly an IM injection, or intravenously directly into the vein, IV.
Oral seems most convenient usually.
Often, yes. But IV is frequently preferred in serious or critical situations. Why? Well, maybe the patient can't take anything orally, they're vomiting, or their gut isn't absorbing properly, perhaps due to illness or surgery. Sometimes intestinal movement is slowed, like with opioid painkillers affecting absorption. Some drugs just don't come in an oral form, and aminoglycosides are a key example. And crucially, in very sick patients, you need high drug levels fast. Oral absorption takes time, even a small delay might be too long. 4V gives immediate, reliable levels. Okay, IV for speed and reliability in critical moments. Now, the unavoidable part, side effects. These drugs are powerful, but they aren't perfect. There can be collateral damage. Understanding this is so important for clinicians. What are the main categories of trouble?
Yeah, definitely need to consider the downsides. First is direct toxicity. These drugs can potentially harm organs, kidneys, liver, nerves. Some can even pose risks during pregnancy, affecting the fetus. This is where concepts like the therapeutic range come in, keeping the drug level high enough to work, but below the level where it becomes toxic. And the therapeutic index, the ratio of the toxic dose to the effective dose. Bigger index, safer drug, generally.
Right, balancing efficacy and safety. What else?
Allergies can be anything from a mild rash to severe life-threatening anaphylactic shock. Penicillin allergy is a well-known example.
And the third one you mentioned earlier seems really significant.
Yes. Changes to normal flora. This is a big one, and sometimes overlooked. Our bodies are ecosystems, home to trillions of generally beneficial microbes. Our normal flora. They help us digest food, make vitamins, even protect us from pathogens. But antibiotics, especially broad-spectrum ones, aren't always discriminating. They can wipe out these good guys too.
Creating an imbalance.
Exactly. And when you disrupt that ecosystem, you create an opportunity. Opportunistic pathogens, which were being kept in check, can suddenly overgrow and cause secondary infections.
So that brings us back to a question posed earlier. Given these potential side effects, especially messing with our normal gut buddies, what's a really crucial thing to weigh up when you're thinking about using a broad-spectrum drug, even if it looks like it'll kill the main infection?
The crucial consideration is actively anticipating and trying to prevent those secondary infections. That disruption of normal flora is a major risk factor. For instance, killing off gut bacteria can let C. albicans, a yeast, overgrow, leading to thrush. Or, much more dangerously, it can allow Clostridioides difficile C. diff to multiply.
And C. diff causes severe diarrhea, colitis, can be really nasty.
Extremely nasty, sometimes even fatal. So yes, you have to weigh the benefit of hitting the primary infection against the risk of causing a secondary one by disrupting the normal flora. It's always a balancing act. Use the narrowest spectrum possible for the shortest effective duration.
A really important reminder, treat the patient, the whole ecosystem, not just the bug. Okay, we focused heavily on bacteria, just briefly. How do we tackle other microbes? Viruses, for instance.
No.
They're tricky, right? Using our own cell machinery.
Very tricky. Because they replicate inside our cells, selective toxicity is much harder. Antivirals have to be clever. They might block the virus from getting into the cell or inhibit its specific enzymes needed for replication, like reverse transcriptase inhibitors used for HIV, or interfere with making viral DNA or RNA, or stop new virus particles from being assembled or released.
More targeted interference with the viral life cycle. What about fungi?
Fungi are eukaryotes, like us, but they have some unique features we can target. The echinocandins go after their cell wall synthesis, which is different from bacterial walls. Amphotericin B targets ergosterol, a sterol in their cell membrane that human cell membranes lack. Azoles and terbinafine inhibit specific enzymes involved in making ergosterol or other fungal components.
Finding those unique fungal features again. And lastly, worms.
Antihelminths.
Antihelminths, yeah. They work in various ways too. Some, like benzimidazoles, mess up microtubule formation, essentially paralyzing worms. Others, like ivermectin or parental pulmonale, cause muscle paralysis through different mechanisms. Niclosamide inhibits energy production in tapeworms, again, exploiting differences between the parasite and the host. Fascinating how we find ways to target all these different invaders. So let's wrap this up. What's the big picture here? We've gone from Ehrlich's dream of a magic bullet to the really complex ways antimicrobials actually work, hitting walls, factories, supply lines. We've talked killers versus stallers, broad versus narrow scope, and the crucial need to consider side effects, especially disrupting our internal ecosystems.
Exactly. This deep dive hopefully gives you that solid foundation, understanding selective toxicity, the different mechanisms of action, the static versus cytal distinction. These aren't just abstract concepts. They're the core principles you use to make real-world clinical decisions, to use these powerful tools effectively and responsibly. It's about patient care, fundamentally.
And maybe a final thought for everyone listening, especially as you head into your medical careers. We're facing a huge challenge with antimicrobial resistance. Bacteria are constantly evolving defenses. So consider this. How can understanding these fundamental mechanisms we've discussed today inspire you? Could it spark ideas for finding the next generation of magic bullets, finding new ways to outsmart the microbes? Lots to think about. Thank you so much for joining us on this deep dive into the world of antimicrobial agents. We'll catch you next time.